Share my screen. Okay, so we were talking about the generalizations of the of McMahon's box formula. So I had stated McMahon's conjecture on symmetric plane partitions. So these are plane partitions inside an A by C box, which are vertically symmetric. And in our language, I think I gave an example. Yeah, so if you write them in this table form, then they are symmetric when transposed. So McMahon gave a conjecture for the number of plane partitions here, and the proof of this turned out to be quite sophisticated. There was not enough technology at that time to be able to prove this, and so I'm going to describe the background needed for this to prove this today. So this is basically a crash course on symmetric functions. So in a way, it's fortuitous that this is happening at the day when most people are forced to bunk the class. So okay, so let me set the stage. So I will go quite fast. I will not prove many of the things. My goal is to introduce all the objects which are needed to be able to prove our results. Okay, so if you need me to prove anything, I can give a sketch of the idea, but I'll probably not prove many of the things. Okay, but let me keep the setting. Let me set the notation and the terminology. So let R be a commutative ring. With identity. So usually we take either Z or Q. Then a formal power series sorry, I need X be an indeterminate. So formal power series denoted R with double box X consists of formal sums of the form f of x, small x, f of x equals sigma n greater than or equal to 0, an x power n, where an belongs to R for all. So we don't worry about issues of convergence and so on. So we just think of this as a formal object, and x we are not going to typically not going to evaluate this at any value of x. So it is easy to see that Rx is closed under sums and products with the identity elements being 0, which is when all these guys are 0, and 1, which is when A0 is 1 and all the other ANs are 0 respectively. Okay, so you can think of one can think of Rx as a completion of the polynomial ring Okay. So this naturally extends this definition naturally extends to the multivariate formal power series ring. So Rx1, x2, etc. xn in the obvious way. But what we want to do is to consider infinitely many variables. So let x now, I'll let x be the infinite tuple x1, x2, etc. So we will consider elements of R x1, x2, etc. R of x, that is, where each summand is a finite product. So we will not allow infinite products for any of the types. Okay. All right. So to state what symmetric functions are, I need the notion of a weak composition. So we'll define it formally. So let n be a positive integer. A weak composition of n is an infinite sequence alpha, which is alpha 1, alpha 2, etc., such that sigma I equals 1 to infinity, alpha I is equal to. Okay, so the weak in the composition just means that you allow zeros, and if you allow 1 zeros, you might as well allow 10 zeros or infinitely many zeros. Okay, so then I can define what a symmetric function is. So a homogeneous symmetric function of degree n over R is a formal power series of the form okay, so let me write it here. So f of x is equal to sum over alpha c alpha x to the alpha, where so medium points and pointers. So alpha ranges over all weak compositions of n. C alphas belong to R. X to the alpha by definition is x1 to the alpha 1, x2 to the alpha 2, etc. Okay. Since it's a weak composition, alpha is a weak composition over n, there are infinitely many zeros in the exponent, so you will so each term will be a finite product, and such that so far this is just a function. This is just a function. So the symmetry says that f of x1, x2, etc. is equal to f of x of sigma 1, x of sigma 2, etc. for every permutation sigma of the positive integers. Okay, so you allow any possible permutation. This could be a permutation of finitely many indices or infinitely many, it doesn't matter. Whatever you take, you should get the same function. Okay, so so that guarantees the symmetry. So the reason for using the term symmetric function instead of a symmetric polynomial is simply because we have infinitely many variables. In many cases, we will deal with finitely many variables, but it's often convenient to think in infinitely many variables because the results generalize naturally, and the notation also becomes more compact. Okay, so we use the term symmetric function instead of symmetric polynomial simply because we deal with infinitely many variables. So even for example, if you are looking at degree 1, there are infinitely many terms. Okay. All right. So so let lambda n r, which is when r is clear, we'll just write it as lambda n, be the set of homogeneous symmetric functions of degree n. So it's clear that if f and g belong to lambda n and a and b belong to r, then af plus bg belongs to lambda n. Right? So this implies lambda n is an R module. And further, if if R is a is Q, then you get to this vector space. If F belongs to lambda m and G belongs to lambda n, then Fg clearly belongs to lambda n plus n because the degree is that. So if we write lambda r as lambda 0 r direct sum lambda 1 r direct sum lambda 2 r direct sum etc. Every symmetric function which is not necessarily homogeneous f can be written as f equals f0 plus f1 plus f2 plus etc., where fi belongs to lambda r. Okay. So then lambda r becomes an R algebra. Okay. Okay. So if R is Q or the real numbers or complex numbers, then this becomes a vector space, and then one can talk about natural bases. There's also a notion of bases for modules, but we can just think for now we can just talk in vector space language. For now, fix R equals Q. In that case, lambda, which is lambda Q, is a vector space. In fact, it is graded. Remember, it is graded by degree. And so, I mean, this is a special kind of vector space, so it's natural to ask for distinguished bases of lambda n, let's say. So it is natural to consider distinguished bases of lambda. So let's do that. So let's do an example. So let's take, for example, n equals 3. So can one of you give me an element of lambda 3?
x1 into x2 into x3, like and take all the.
So right. So let's say first example. So f1 is what? x1, x2, x3. So this has degree 3, and then you take whatever symmetric. I mean, you act by this on all possible sigmas as right? So x1, x2, x4 plus etc. And then x2, x3, x4 plus x2, x3, x5 plus etc. And so on. So this is if I write it succinctly, this is xi1, xi2, xi3, 1 less than or equal to I1, strictly less than I2, strictly less than I3. So sums over all those guys. Okay, that's one. Any other element?
x1 cubed plus x2 cubed plus.
Very good. So f2 is what? X1 cubed plus x2 cubed plus etc. So this is even more simpler to write down. So this I going to infinity xi cubed. Anything else?
There are terms like x1 square, x2 plus all
Right.
this symmetric parts.
Right. So you get things like x1 squared x2 plus x1 squared x3 plus etc. plus x2 squared x1. You should also take that plus x2 squared, but you should not take x2 squared x2 because it's already here. Well, you could if you wanted, but x2 squared x3 plus etc. So if I write sigma 1 less than equal to I1 comma I2 infinity x I1 squared I2. So I should I1 not equal to. Actually, I could do that also. Okay. Yes. So these are all three in some sense. Any other oh sorry elements. Okay, so I claim that any other element of lambda 3 can be written as some combination of these. You might have already seen that before. Okay, so what is the what is the point? So if you for n equals 3, we have three kind of distinguished elements, and these form the basis. And for n equals 2, you can easily reduce this in the obvious way. There will be x1 squared plus x2 squared plus so on, and then you will have x1 x2 plus x1 x3 plus so on, and that will be it. So there will be two elements. And when n is 1, there's only one element, which is x1 plus x2 plus 1. So so for 1 you get 1, for 2 you get 2, 3 you get 3. So it's natural to think that for n equals 4 you will get 4 elements, but actually you will get 5. And the idea is that the indexing set for for a basis of lambda n is the set of partitions. And so that leads to the first let me not say this definition. The first set of the first distinguished basis, in some sense, the simplest ones are called the monomial symmetric functions. So these are the analogues of monomials in the polynomial ring. So I've already defined partitions, so I'll not do that again. So given a partition lambda of n, define the symmetric function lambda, m for monomial. This is the sum over alpha, x bar alpha, alpha equals alpha 1, etc., where alpha is alpha runs. So alpha is a weak composition which sums to n, where alpha runs over all distinct permutations of lambda. Okay, so this alpha is a weak composition. So you take lambda and you run over all of these weak compositions. So then the proposition is that m lambda, the set m lambda, lambda partition of n, as lambda ranges over all partitions of n, is a basis. Okay. So so going back to the example above, here F1 is M of 1, 1, 1, because this is the partition 1, 1, 1. So each variable appears exactly once, and there are 3 of them, and that was the first example over here. F1, sorry. F2 was the partition where there was only one exponent, which was 3, and so this was M3, and F3 was the partition corresponded to the partition where one exponent is 2 and one exponent is 1, and this is M2. Okay, and these are naturally, so the examples you gave naturally fit in this category. So I wanted to also show you on Sage how these work, or maybe I'll do it later. No, okay, we can do it. So in Sage, you can symmetric functions are defined using this command. So you take symmetric functions and you define the ring or the field, whatever you want to work over. So we want to work over the rationals. So I've defined sim this way. I can define variables for each of the classes of symmetric functions that I'm going to take. So you can ignore the others for now. So let me. So this in one shot defines all the symmetric functions, all the standard symmetric functions for me. So if I take m to 1, so the notation is you put you put one of these letters, which other ones I'll define soon. So this m is for the monomial basis. So that's what we're going to work over. So m to 1 is the symmetric function in the variable, for the partition, indexed by the partition to 1, and you can do many things with it, but for now let me just show you I can do it over here. So if I use the phrase expand, it will be often useful to us to restrict the number of variables, as I said earlier. So suppose I just want to see how it looks like in 3 variables, then M21 looks like so. As usual, say indexes starting at 0, so I have x0 square x1, 0 x1 squared, etc. So I have 6 terms, and I can do more. So we can look at all 3 of them, for example. So let me not do so. So M21 I have done. Then I can do M3, this one, and then M1. So in this case, there's only one. Yeah. Okay, so this is the most basic and in some sense the most boring symmetric function. I mean, the way to build it is to just take a monomial like you naturally would, and then act by all possible permutations of the variables, and you will get monomial symmetry. Okay, so as I said, it's easy to show that this forms a basis, and as I said, I'm not going to give all the proofs because this is a crash course. But if you need me to expand on anything, I can do so. All right. So right. So the next symmetric function is a little more interesting. Is I mean, the next basis rather is called the elementary symmetric. Okay, so let me first. So as I said, the indexing set for the basis is the set of partitions. But first, let me define what. How to let me first define it when there is a single index. So for n in n, let En, okay, this is without brackets, so it's just indexed by an integer. This is the same as m of 1, 1, 1 n times. Okay, and written more elaborately, this is 1 less than equal to I1 less than I2 less than up to In, xi1, xi2, etc. Right. So think back to this example as and generalize it. So that's what gives you what are called the elementary symmetric functions with E0 is 1. Okay, so then this defines E sub a single integer, non-negative integer, and for lambda equals lambda 1, lambda 2, etc. Lambda k, maybe we say. Define E lambda. Now it's indexed by partition is just E lambda 1 times E lambda 2 times up to E lambda k. Okay. So for example, let's look at n equals 2. So we are looking in 2 variables, and we are looking at degree 2 in 3 variables. So 3 variables, let's say. So I mean, I'm just doing this so that it's convenient. So E of the partition 2 is just E2, right? And this is x1, x2 plus x1, x3 plus x2, x3. And E of the partition 1, 1 is just E of 1 squared, because this is E1 times E1. So that is x1 plus x2 plus x3 whole squared. So this is going to be equal to x1 squared plus x2 squared plus x3 squared plus twice x1 x2 plus x1 x3 plus x2 x3. So I should have mentioned, maybe I'll do that carefully. So this is E of 2 of x1, x2, x3. Okay. When I don't write how many variables, you should assume that they are infinite. So E2 of x1, x2, x3 is that, and here also I'll write it carefully. E11 of x1, x2, x3 is E1 of x1, x2, x3 whole squared. And now you can see, if I write each of these in terms of the monomial symmetric functions, this one is exactly M11 of x1, x2, x3. Right? It's just with analogy here. So that's that. And here, this is M2 of x1, x2, x3 plus twice M11 of x1, x2, x3. Okay. So in three variables, you can see that E2 is M11 and E11 is M2 plus 2M1. But the interesting thing, and this is what makes it so useful to work with infinitely many variables, the interesting thing point is that this expansion is identical in arbitrarily many variables. For example, if you had just taken two variables, then this would just be x1, x2. So that is M1 over there in two variables. And here you would have x1 plus x2 whole square, which is x1 square, x2 square, 2x1, x2. So again, you would get the same expansion. But you can easily check that you take any number of variables, it's true. So E2, E of 2 is actually M11, and E of 11 is M of 2 plus twice. Okay, and this is easy to do in Sage. So here the E is the elementary symmetric function. So in Sage to express let's say E in the M basis. So okay, maybe I'll start by doing the obvious. So E of 2 is E2, okay. But if I expand in three variables, I get that. And if I do E of 1, 1, I get what I just wrote. But now if I want to express the E's in the M basis, Sage knows how to do it without specifying the number of variables. So if I do M of E2, I'll get M11. This is what I just wrote over here. E2 in the M basis is M11. And M of E11 is 2M11 plus M2. Okay. Similarly, one can write down so one can express E lambda as lambda ranges over all partitions of n in terms of n mu, where mu ranges over partition. Okay, and so this also Sage can do. So I can show you how to do that. So I have to remind myself. So if I write E dot transition matrix, so I've forgotten the syntax. So let me check. So I have to write E dot transition matrix in terms of the m in the number of variables. Okay, so that it takes 2 arguments. So let's do that. So if I write E dot transition matrix in terms of m, not into, sorry, I beg your pardon. It's not number of variables, it's the degree n over here. So I want degree 2. So I get this as the basis. So what this is saying is it's indexing. Let me show you the. So if I list the partitions of 2, so the row first one is saying E2 in terms of m. So it's 0 times m2 plus 1 times m11. That's the first. And the second one is saying E11, the second row is saying E11 is 1 times M2, that's this term, and 2 times M1. Okay, so it's so Sage is naturally indexing the rows and columns by partitions, and the order of the partitions is specified. If you want to see what the order is, you just do list of partitions. Okay, so let me copy that. Okay, so let me do in 3 variables. That's it. So now you see now it's using this, and you seem to get something that is lower triangular about the anti-diagonal, something like that. But I don't think that's okay. So yes, so that does work in general, I think. Yeah. So let's take higher, and you will see that along the anti-diagonal you will always have ones. Above it you will have zeros, and below it you will have non-zero entries. So you know this says that you can I mean the E lambdas also give you a basis. So this proves this the result that I mean it doesn't prove, of course, but one can show this thing, and yeah. So sorry. So it doesn't quite work. Yeah, that's what I thought. But this has to do with the fact that if you expand E lambda in the m basis, you will get the coefficient of 1 for lambda prime, the conjugate partition. So here we can see where that fails actually. So for 6 we can see. Let me show you. So m of E. So E of. I have to take the 4th partition, right, which is 4, 1, 1. So let me do that. So if I do 4, 1, 1, I'll get 3, 1, 1 as the first term, but that's not the 4th term from bottom. That's the fifth term, and that's why you are getting. Sorry, that's why you are getting a 1 here. The fifth from bottom instead of fourth. Okay. So you won't in general get this property that I said, but it is possible to show. I mean, a little more combinatorially. I'm not going to do it. That E lambda or lambda partition of n is a basis. Okay. But there is one property that I do need later on, so I think it's best if I show it over here. So consider or maybe I'll just write it as another proposition. Let E of t, okay, let t be another formal variable, and E of t be the formal power series now, n greater than equal to 0, En in x1, x2, etc. So in infinitely many variables, t power n. Then E of t has this product formula, n equals 1 to infinity, 1 plus xn. And this is kind of easy to show. If you take the coefficient of t power n, you will get n of these guys in all possible orders, and therefore that will be, if you sum over those, and you will get precisely E. Okay, so that's easy to show, and I'm not going to say more than that. Okay. So another. So any questions about this? Okay, so I've defined two bases so far. Okay, so the third basis that I need are called the complete symmetric functions. And some people also say complete homogeneous. Again, just like for elementary symmetric functions, we will first define them for integers with the index by the integers. So for n and n, let hn. So h stands for homogeneous, but it's really the complete symmetric functions. So this is the sum over all partitions in n, of all partitions lambda in n of the n lambdas. Okay, so you take all possible guys and you take their sum. And expressed in another way, which resembles how we wrote it for the elementary symmetric functions. This is I1 less than or equal to I2 less than or equal to I3 less than or equal to In. Okay, so let me finish. So this is xi1, xi2, etc. with h0 again equal to 1. Okay, so if you compare with the elementary symmetric functions, you see that there was I1 less than I2 less than up to In. Here it's less than or equal to. Okay, so you're allowing repeats, in other words. Okay, so again, let me do an example. Okay, so to complete the definition, let me write it in the same style as I did before. So for lambda equals lambda 1, lambda 2, up to lambda k. Let h lambda, now it's indexed by partition, it's just h lambda 1, h lambda 2, product up to h lambda k. So let me go back to the same example. N equals 2, 3 variables. So h, again let me write it carefully. So h of the partition 2 in x1, x2, x3 is m of the partition 2 x1, x2, x3 plus m because h of 2 is just h2, right, from this definition. So I'm going to sum over all those guys. This is plus m11 x1, x2, x3. So you see the basis expansion already. So you get x1 squared. So if I go from this definition, you get x1 squared plus x1, x2 plus x1, x3. So I fix I1 to be 1, and then I range over all I2 greater than or equal to I1. Then x2 squared plus x2, x3. This is when I1 is 2, and then I1 is 3. So then I2 is supposed to be 3. Okay. And now you can see that these terms correspond to M2 and these terms correspond to 1, 1. So that is H2, and H11 of X1, X2, X3 is M1, which is H1, X1, X2, X3 whole square, which is X1 plus x2 plus x3 whole squared, which we have seen before as E1. Okay, and so let me show you how these look like. So this was also defined in the shorthand. So it's H in the homogeneous basis, which is the same as the complete basis, as I said. So let me do that again. So H of 2, okay, there's nothing to do with that. If I do M of H over 2, I get M11 plus M2. This you notice is different from E2. And M of H of 11 is, because it's E11, it's the same. Okay, so I can sorry, I can copy that, and now I can show you the transition matrix in the M basis. So this is what I said. So it's 1, 1 and 1, 2, and the partitions are indexed. I mean, the first partition is 2, and then it's 1, 1, as you can see. So H2 is the first row, and H11 is the second row. And similarly, we can go higher. So if I take 3, 4. Now you see all the entries are non-zero, and so it's a little more tricky to prove that this matrix is invertible. So if the matrix is invertible, because we know that M's form a basis, then we can show that H's form a basis. So it's a little different, little more tricky to show that this is a basis, but one can do it. So so here's the position. H lambda partition of N is a basis. Okay. Any questions about this? Okay, so analogous to this proposition for elementary symmetric functions, we have a similar result here. So this will also prove useful later. So let, as usual, t be a formal variable. And h of t be this generating function n greater than or equal to 0, hn of x1, x2, etc. times t power n. Then h of t is the product n equals 1 to infinity 1 by 1 minus xit. So if you compare here this, oh sorry, xnt. So here it is 1 plus xnt in the numerator. This is 1 by 1 minus xnt. Okay, and again, if you expand each of these in a geometric series and you combine terms, you collect terms proportional to t power n, you will see that there are, of course, the degree of the terms will be n, and you'll see all possible terms and conversely. Okay, this is not sufficient. So in particular, this shows that h of t times e of minus t is equal to 1. Because if I set t to minus t over here, I'll get 1 minus x and t, and that cancel this. Okay. Okay. So that gives me the third basis. Now I can talk about the fourth basis. These are the power sums. So I should have noted one thing which is maybe not so obvious, which is that the transition matrices for E to M and H to M both consist of integers. This is not obvious a priori. Yeah. It's not terribly hard, but it's not immediately obvious. Okay. So the power sum symmetric functions. So in other words, the previous two families, all three families could be defined happily over Z. When we said take the ring to be Z instead of Q. This one will turn out cannot be done. I mean, is not so nice in Z. Okay, so following the tradition of the last two symmetric functions, we will define these over the integers first, and then over the partitions. So for n and n, so these are denoted by p. So Pn is the monomial symmetric function for the partition n. And so this is sum over I, so infinity xi power n. And with p0. Okay. And again, for lambda for lambda equal to lambda 1 into lambda k, let P lambda be P lambda 1, P lambda 2, etc. Okay, so this defines the power sum symmetric functions. And again, let me go through the same example as before. N equals 2, 3 variables. So P of partition 2 of x1, x2, x3 is P indexed by integer 2, which is x1 squared plus x2 squared plus x3 squared, and P indexed by the partition 1, 1, x1, x2, x3 is x1 plus x2 plus x3, because this will be p1 times p1, so it's x1 plus x2 plus x3 whole square, which we have again seen. This was e1. But now let's try and express this in terms of the monomial symmetric functions. So what was okay? Maybe we'll do it directly on stage, and instead of my making some mistake. So this is also defined automatically. So this is the power sum basis, and P is the shorthand. So let's write P of 2. Okay, so that's not a problem. Now let's express M in terms of P of 2. This is M of 2. That's okay. And what is M of P of 1, 1? This is 2m11 plus m2, which is the same as before. This is the same as this. And so if I expand P in the M basis, we get this matrix, and we can again go larger. So in 3, and 4, and 5, and so on. Okay, but now let me show you why there's a problem. I mean, why I made the remark that P's are more naturally defined over the base ring being the rationals instead of the integers. Let's go the other way. So now that I've defined these three, and we can go the other way. So let me write M in terms of first the elementary symmetric functions. Let me go a little higher. So now here you see we have essentially taken the inverse of a matrix like this, and here you find integers. Okay, not necessarily positive. I can go higher. Let me go to 6 to show you. And now let me write this for the homogeneous symmetric functions. Let's go slow. So remember, in the homogeneous case, all the entries are non-zero. So you're going to get some mess in the calculation, but this still turns out to have integers. But now let me do it with P. And now you see you'll start to get fractions. You'll start to get rationals. Even for 3 you'll get it. And even for 2 you'll get half because of this determinant being 2. So here you see it was not, I should have mentioned earlier, that the determinant of all these matrices is 1. Here, but not anymore. If you go high, you'll get even more complicated expressions. But we do know what these denominators are. In fact, the LCM of these denominators will be this last entry. And that has a well-known well-known interpretation. Okay, so, but here also one can prove proposition that P lambda partitions as lambda runs over the partition of n is a basis. Okay. What else I want to do? Right. I want to understand. Okay. So I certainly want to define one more or the most important symmetric function after this, but I want to define two other structures on lambda n, and this is going to be a little unmotivated, but you have to sort of bear with me that these are important and in some sense naturally defined objects. So I want to define a scalar product. So we endow lambda with a bilinear form which goes from lambda plus lambda to, in our case, q by required okay, wait, let me just set some notation. If u lambda and v lambda are bases of lambda such that q lambda v mu is delta lambda mu, then we say that u lambda and v mu are dual bases. This is just some general notation and general terminology. So we define by requiring, so our definition in some sense is going to our definition is going to give dual, is going to prescribe dual bases. So by requiring that m lambda, so this is, as I warned you, is going to be completely unmotivated, and h mu are dual bases. By requiring these two be dual bases, i.e. m lambda h mu is equal to delta lambda mu for all partitions. Okay, so So one property of this is which might make it more palatable is the following. I need to define something. So for lambda partition n, okay, for lambda partition, write lambda in frequency notation. I don't remember if I've used this before, but I'll state it again, if so, as 1 to the m1, 2 to the m2, etc. Where mi's are non-negative integers. Okay, so what it's doing is it's counting the frequencies of each of these entries. So this means 1 occurs m1 times, 2 occurs m2 times, and so on. Okay, and we write angular brackets to distinguish it from the usual partition notation and to not get confused. Then define z lambda as 1 power m1 times m1 factorial times 2 power m2 times m2 factorial, and so on. So this is the product over all I to the mi times mi factorial. Okay. So here is a standard result which you can derive. Theorem. Maybe I'll leave it as an exercise. Show that the number of permutations in Sn with cycle type lambda is n factorial divided by 0. So cycle type means you write permutation in cycle notation and form a partition from the lengths of the cycles. Cycle lengths. Okay. So this also has a group theoretic meaning. This is the cardinality of the centralizer. So in Sn. So this is an important sequence. Okay. So the proposition, which may be about the scalar product, is that p lambda, p mu. So p lambda is an orthogonal basis. So p lambda, p mu is z lambda delta lambda. Okay. That is p lambda is self-dual, so they form an orthogonal basis. But not orthonormal. So I should have said this is called the Hall inner product, sometimes called the Hall. Oh boy. Okay. So I think I'll need one more. I'll need to take half the lecture more to define the next object, the next symmetric function. But let me, as I said, I need one more notation, one more structure on lambda, and that's an endomorphism. Again, this will seem arbitrary. So, but this, okay, so define omega from lambda to lambda. So, by its values on En as omega of En is Hn, and extend to all of lambda by using, by the algebra structure. So it's an algebra endomorphism, the algebra structure on lambda. That is to say, omega of E1, E2 is omega of E1 times so. So then the theorem is that omega is an involution, and so omega of Hn is En. Right? And again, as I said, this is not well motivated. I'll come back to this definition once we have a little more data or a little more information about lambda. So, so how does omega act on the p lambdas? I need another bit of notation. So for lambda in frequency notation again is 1 power n1, 2 power n2, and so on. Let epsilon lambda is -1 to the n2 plus n4 plus etc. So it's really the sign of the permutation. Or maybe not quite. Which is -1 to the n minus length of lambda. Right. So it's almost the sign. No, wait a minute, I'm getting confused. Right. Let me not try this. For a permutation which has cycle type lambda, this is exactly the sign of the permutation. So if sigma in Sn has cycle type lambda, I just defined the cycle type earlier, then this is the sign. Okay, so then, so the result is that omega of p lambda partition lambda, omega acting on p lambda is epsilon lambda. So P lambda is an eigenvector. Omega with eigenvalue. The one other property of omega as it relates to the inner product is this nice property that omega is an isometry. i.e. omega f omega g is omega f inner product omega g is inner product fg for all fg. Okay, so so these two structures, this isomorphism, this endomorphism and this inner product, are not completely random objects. Okay, so I want to do some more things, so maybe I don't want to start a new topic now, so maybe it would be good to stop. But let me motivate two questions. Let me motivate the next, the most important basis of lambda by two questions. One, so from this inner product point of view, we have not yet seen an orthonormal basis. P lambdas come close, they are an orthogonal basis, right? But this guy is not one. So the question is there a natural orthonormal basis in lambda? And number two, is there an integral orthonormal basis in lambda, i.e. Z, let me give some name, let's say B lambda, i.e. B lambda is Z linear in N mu, and M mu is also Z linear in B lambda. Okay, so that's the question. So it turns out that there's a positive answer to both by the same class of symmetric functions, which I'll talk about next time. But let me show you how these inner products and all these things act. I mean, are coded in Sage. So I think so. Let me just define something. So if I take f equals m to 1, I do f dot, can I do scalar? Yeah, so this is the Hall inner product, as I said, standard scalar product. And we can take this scalar with f itself. So this gives 5, and so what we can do is construct the matrix of all scalar products of m lambda to m mu. So let's say matrix m lambda dot scalar and mu for mu in partitions for 3, for large partitions 3. So here's how it looks like. So this is for the monomial basis, but one can do one can do. So one can check the defining property, which was what you remember. It was that m lambda and h mu are orthogonal. So now you can see that this gives the identity matrix. This was the definition. One can do, let's say p lambda p mu. So you see that this is orthogonal, but not orthonormal. And one more, h lambda with h mu, e lambda with e mu. Okay, it looks very similar. Yeah, and so on. So you can also do e lambda with h mu. You can try to get other things. But yeah, so so I think this is a good time to stop. Are there any questions? So since most let me stop recording. Oh, okay. Are there any questions? Okay.